Yo, what's up, people? This is Robert Bassano. I want to thank you guys for coming in, being up late. For those who are over in Europe, those who are in the U.S., it shouldn't be that late at all. You guys know my motto, right? It's not what you know, it's what you can prove. If everybody can hear me out there, I think you can. I'm watching the watch page right now. Some people are saying, what's up? So if you can hear me, just a quick little thumbs up would be appreciative. I was going to have John in here, but I guess he had the family duties, so he's not going to be with us tonight. But I'm going to go through a document review regarding detection of the ether. We're going to specifically talk about the speed of the moon. This document was actually put together by a private researcher. I have since emailed this individual. His name is on the document. And we're going to talk about a few things. I got another associate in here with me. His name is Vivian, and he lives here in Colombia as well. He's been here a little bit longer than me. We had a nice little family outing in powwow, and he's going to be contributing to the conversation as well. But I'm going to go through and read this document for you guys, and we're going to discuss some things that Vivian and I talked about it. John and I talked about it. I talked about it with a few other people, and it kind of baffled me a little bit. So we're going to go through some other things as well. This is probably going to be about an hour, maybe an hour and a half. I'm not going to make it too long. So, but I'm not going to be watching the chat, people. So, oh, wait, Robert, I have a quick question. Did the math teacher ever get back to you? Which math teacher? Flat Earth Math? He and John have been having that back and forth powwow. I don't know why he didn't want to do a follow-up on his own channel. The dude's put up videos before, but I don't know what the deal is. So I was watching a conversation in chat. Those two commenting on those shows that they did, and it just was one of those things to where he and John were going back and forth. If they wanted to do the thing, they could have did it. I'm not running some circus here. So, you know, I like sticking to the model. It's not what you know, it's what you can prove. And he wasn't presenting too much of anything for me. The best to him, but if he wants to continue that thing on with John, he knows he can do it on his own channel. Okay? So, to no further ado, let's get to this, okay? I'm gonna pull up. Yeah, I'm watching there, big brother. You need to mute there, big brother. John's in here now, so. All right, so what I'm going to do is I'm going to share my screen. We're going to go through this document. It is a document review. So here's what I'm going to do for you guys. And I need for John, Vivian, if you're looking at the watch page, let me know if everyone can see the screen. And we'll begin this, man. We'll start this up. And just so that you guys know who this document was actually put up by, and I'll show you who it is. The guy's name is R. Webster Kerr. You can look him up, Google him. I know he's doing some research into cancer and stuff like that. You know, I'm not going to judge the guy, what it is he's doing, what he's not doing. But I will say this. I have contacted him to see if he'd be willing to do a follow-up and we could actually talk about this with him. And if we can, you know, I've got some questions I want to ask him. So this is the guy here, detection of the ether. He did a lot of his own experiments, a lot of his own research. I like that. And but of course, we've got some questions we have for ourselves, and we were working to make sense of this. And again, the title of this hangout is Detection of the Ether, Speed of the Moon. I put a question mark to it. Okay? Now, here's what's interesting about this. Here's discussion on lunar laser ranging experiments. It's chapter 10 of the document. Okay? Um, he goes on to talk about the tilt of aberration for the interior planets. One of the things I really wanted to know was the tilt of aberration for light from the interior planets. Okay? I'm not going to get into a conversation and debate about if planets do or do not exist. I know that right now I'm just going off of what I can see, what I can observe. All right? I don't know what the hell is in a telescope. Could be Mars, Jupiter, or whatever it may be. Whatever the hell it is, okay, we just can't get a really good picture of it. Okay, a really good view of it. All right? So I'll leave it at that. Again, you guys who are in the hangout with me, pay attention to what's going on in chat. Because if those people have questions about what they're seeing and what I'm saying, you guys are the ones who can answer those questions for those guys in the chat. Okay? So I need you paying attention to the watch page. All right. So as I go through this document here, I'm going to start at this section here where they talk about what happened in 1969. Now, everybody's going to say, yeah, Apollo, you know, we never went to the moon. All right. For argument's sake, I'll go with that. But for the immediate conversation, we're gonna assume, okay, something went out there. Did they travel 256,000 miles or 348 kilometers? Absolutely not. Okay, nothing went 200,000 plus miles in 1969. All right, it's much closer. But we're gonna go over that as we speak. All right, in this document. They're talking about how Apollo 11 astronauts placed a small box on the moon's surface. This device was a very special type of mirror, a retroreflector. Because it was placed on the moon, it is frequently called a lunar retroreflector. What is special about a retroreflector is that it reflects light back to its point of origin. Now, here's what I want to do for you guys. I want to show you what that looks like. And here's your laser lunar reflector. This is it. They say it's about the size of a suitcase. Okay? Maybe a carry-on. This is that laser lunar reflector. This thing right here. This is phony as hell, this mirror. Okay? It shows this guy carrying this, whoever the hell it is. They supposedly got several of these. I don't know, you know, how many of these they actually put on the moon, but apparently, however many they put there, this is what this thing actually looks like. It's the size of a suitcase. Okay? That's what they're saying. There goes another photo. Oh, I'm sorry, pulled up the wrong photo. Here's a photo where they claim they shot a laser at the moon. Now, I'm not going to get too much into how lasers work and, you know, what their capabilities are, but let's do this based on logic here. Okay? When we look at this diagram right here, it says outbound pulse starts at 3.5 meters in diameter, 2 centimeters thick. Atmosphere causes beam to diverge by 1 arc second or more. At the moon, 1 arc second is 1.8 kilometers, so beam at the moon is about 2 kilometers across. Only about 1 in 30 million photons in this 2-kilometer beam hit the suitcase-sized reflector. Each outgoing laser pulse contains 300 quadrillion photons. Okay? Returning beam expands due to corner cube diffraction. Returning beam divergence is about 8 arc seconds. Return beam footprint on Earth is about 15 kilometers across. About 1 in 30 million of these returning photons hits a 3.5 meter mirror. Okay? This is what they're describing here. All right, and this came from the University of Southern California, UCSD. I went to this university. All right, took a few courses there. This is physics at UCSD. The basics of lunar ranging. All right, I'll put this in the link for I'll put this in the description section for you guys so you can refer to it. But let's go back to the document. So everybody saw what the size of that reflector is. So now you know what the lunar retroreflector is, okay? Now he goes on to say, to understand this, note that a normal mirror will reflect a 15-degree light ray away from the point of origin, meaning the light will exit the mirror at 15 degrees away from the point of origin. But a retroreflector, which actually consists of an array of grid of corner cubes or corner reflectors of mirrors, returns light back to the point of origin. So they want us to believe, I'll tell you what they want us to believe. Let me see if I can get a better picture of this damn thing. All right? Here goes a picture of this thing. This is a picture of the sensors. I'm sorry. This is a picture of this thing. Let me see if I can get a bigger picture. Trying to see if I can get a better picture for you guys. Stand by here. Can't get a better picture of it for you. Let me see here. This might be the same thing. Yeah, that's the best I can do for this thing right now. Well, hey, this might be a better one. Nope, that's not it. Okay, so this is what it is. These are supposed to be these little tiny cube reflectors, all right, that send the light right back to the source of origin. That's what they said. That when a laser beam is fired from the Earth, from whatever observatory, somehow, maybe 1 in 30 quadrillion photons hits this thing, and it goes back to the source of origin. Personally, I think that's a bunch of bullshit. That's me. You don't have to believe it. I think it's bullshit. You're trying to tell me the moon is 258,000 miles away, you can fire a laser beam, okay? Fire a laser beam from the surface of the Earth, travel 258,000 miles, it's going to hit something the size of a fucking suitcase, and come back within 2.5 seconds. Okay? That's what they're saying what the refraction of the light is, the reflection. All right? Now, this guy goes on to say that if you fired a laser at the retroreflector, the beam would come back and hit you. A retroreflector does not reflect light at an angle, as a normal mirror does. A retroreflector is specially designed to send light back to where it came from. That is why we know exactly where the retroreflector aiming is reflected light. They're saying in total there are 5 retroreflectors placed on the moon between 1969 and 1973, but only 4 of them are functional. The largest of these retroreflectors and one of the most often used in the lunar laser range experiments was left by the Apollo 15 astronauts in 1971. And here they go. The retroreflectors are generally about the size of a small suitcase. Now that's a fucking carry-on that you take on the plane. 258,000 miles away. So what John and Vivian and Robert Shortman and I have been thinking about is how powerful does that laser need to be? Okay? To literally hit something the size of a fucking suitcase 258,000 miles away. Now I want you guys to all think about the logic of that. I want you to really think about the logic behind that. You got a carry-on suitcase, all right? Well, it said small suitcase. It didn't say a large suitcase, small. So let's just say you got a normal carry-on on the fucking moon, 258,000 miles away. Let's just, for argument's sake, I already did a video saying it's not there at that distance. But let's just say, for argument's sake, we want to tickle NASA's balls, okay, and say, yeah, we agree with you. They're saying they got something on the moon the size of a fucking small carry-on suitcase with these small little corner cube reflectors, and they can fire a laser beam, and that fucker goes right back to where it came from. The beam doesn't get bigger and spread out. Now, where there's a contradiction in terms here is the fact that they went and said, what did they say here? Okay? They're saying that this fucking thing is hitting, all right? They said 1 in 30 million of the returning photons hits a 3.5 meter mirror. 1 in 30 million. They said the outgoing laser pulse contains 300 quadrillion photons. I can't even comprehend fucking how much that is. That's probably about smaller than a fucking penny. Right? When you think about what the size of a photon is, it's probably about half the size of a fucking penny, 300 quadrillion photons. All right? But returning back, only 1 in 30 million of returning photons hits a 3.5 meter mirror. Okay? The round trip is 2.5 seconds. So we're trying to figure out how strong, how powerful is this laser? How powerful is this laser? Because this laser would have to be pretty damn powerful to hit something at 258,000 miles. Or it goes back to the video I already did that's getting crazy comments. This moon is not 258,000 miles. This moon is closer. This moon is way closer. Okay? It's somewhere between, I'd say it's somewhere between 90 to 200 kilometers. It ain't 258,000. It ain't 348,000, which is the equivalent to 258,000. 348,000 kilometers is 258,000 miles. Period. Okay? So let's keep going through this. They're saying the major purpose of the LLR experiments is to determine various facts about the relationship between the moon and the Earth and to learn some specific facts about the Earth. For example, measuring the time it takes the laser pulse to make the round trip between the Earth and Moon at different times of the day can yield very accurate measurements of the distance between the Moon and the Earth. This assumes the speed of light is a constant during the trip, which is an assumption that will be discussed much later in this book. Okay? They're talking about the angle of beam divergence, where the beam actually gets smaller instead of getting bigger. That's a bunch of bullshit as well. That had to be a really powerful beam, or there's some sort of medium between the Earth and the Moon. That's why this document is titled Detection of the Ether. You know, all of the physicists, Einstein, Max Planck, Henry Lorentz, they all discussed detection of the ether. Even Tesla discussed trying to detect the ether. No one knows what it is. They know it's playing some sort of, it's needed for signal transmission, electromagnetic wave transmission, and propagation. So somehow the ether is playing a role in allowing for beam divergence. Okay, this guy says when light normally leaves a laser, the angle at which the light leaves the laser is frequently very high, perhaps as high as 30 degrees or more, depending on the laser. This angle is called beam divergence. Okay, so you got a concentrated laser, and then all of a sudden it just loses its ether drag, so to speak. What other environment's going in? Who knows? We all know that when the European Southern Observatory fires a laser up into the sky to create artificial stars, they're hitting a sodium layer of atoms between 90 and 110 kilometers. Okay, that's just above the Kármán line. Now it's got to be a powerful laser down in Chile, but it's hitting something. It's not. It doesn't keep going at all. And he says, think of a flashlight. If the angle of light from the flashlight, the angle formed by the two sides or edges of the outside of the main beam was 0 degrees, meaning the edges were parallel, then 100 yards away, the width of the flashlight beam would be the width of the flashlight lens. But that is not the case. The light from the flashlights and some types of lasers is very broad, meaning that 100 yards away, the beam might be 30 yards wide or more. When the angle of the light that leaves a laser is too high, the lens or mirrors can be used to make the beam divergence angle smaller. When that happens, the size of the beam is wider, but the beam divergence is smaller. That is a trade-off. You can have a narrow beam coming out with high beam divergence, or you can use a small kilometer and have a wide beam coming out, but with small beam divergence. Now, again, this always is going to come back to how strong is that laser. Because they're trying to hit something the size of a small suitcase. They claim that object is 258,000 miles away. So the complexity involved, or the simplicity that may exist, brings us to one conclusion. The moon is not 258,000 miles. It just can't be. Because we don't have that type of technology to be able to hit something that far away and have it come back in 2.5 seconds. Okay? And here's the irony of this. Do you know that radio operators, amateur radio operators, claim that they can bounce signals off of the moon at the same time that a laser beam can shoot a laser at the moon and it come back 2.5 seconds? Amateur radio operators are claiming they can bounce a signal off of the moon and it takes 2.5 seconds. That's what they say. Okay? So let's keep going through this, all right? I want to get to the meat of this thing here because they're going to discuss the speed, okay? But the way they discuss it is just weird and funny because I criticized this document when I first read it, but then when I started to look at the background of the guy who actually drafted this document, I realized, you know, this is not his area of subject matter expertise. Yes, he has a lot of knowledge in this. He's got a degree in mathematics. He does study the sciences, and he put in a lot of work to put this document together. But I started to really criticize what he was saying in this document, thinking that he was some sort of physicist, and he's not a physicist at all. Okay? So let's let me go to the one part where he talks about laser finding. Introduction to problems introduced by lunar laser ranging. Okay. Now I want you guys to pay attention to something here, because if you're out there in chat, I need for somebody to tell me where the hell Leo is, the constellation Leo. All right? But I'm going to probably find that in a second, well, in a little bit through this presentation, as we go through this, because I found some software that, courtesy of NASA, gives us. Let's just put it this way: you guys are going to laugh when you see the software. You're going to laugh. Okay? So let me see here. Where was that? Okay, so here we go. Here's the scenario. Let me see here. Okay, this scenario means that the Earth and Moon are nose to nose as they are both headed towards Leo. Okay? Note, we can ignore the orbit velocity of the Moon around the Earth and the rotation velocity of the Moon because they are so slow. Now, pay attention to that when you say it's slow. So we're not going to be concerned with how fast the Moon is moving. When we discuss the speed of the Moon, we're not talking about how fast it's moving around the Earth. We're talking about literally the speed of the Moon. Now, some of you are going to disagree. Oh shit, wait a minute, Robert. You're trying to say that the Moon is actually moving, spinning around? And a lot of you disagree with that, because you can look up the Moon, if you can see it right now, if you've seen it, you know, in the past couple of weeks, it looks stationary. Okay, it don't look like it's rotating at all. Okay, I saw the Moon after I got this document. I took a walk with my family. We were looking at the Moon, and you see the same face of the Moon every fucking night. You can see it. It don't look like it's moving at all, right? It's the only celestial body that you can see where it looks like it's not rotating. But according to this guy, it is. All right? He says here, with this scenario, let us visualize what happens when an LLR experiment is done. First, a laser beam is shot at the Moon and the retroreflector. During the time it takes a laser beam to travel to the Moon and back, about 2.5 seconds, both the Earth, this is what he says now, both the Earth and the Moon as part of the solar system move about 948 kilometers towards Leo. Okay? Towards Leo. That's what he's saying. 940. So in 2.5 seconds, The Earth and the Moon are moving in unison 948 kilometers. Now, for all you Americans out there, let's do this, okay? I ain't doing this shit in my head. Kilometers to miles, okay? Let's do this. Kilometers to miles. So we got 948 kilometers in 2.5 seconds, right? That's 589 miles. Okay? That's 589 miles. So we got that math down. Now he says here, so I don't give a, for me, personally, I don't give a fuck where Leo is. Some of you may think, may say, okay, yeah, all right, in 2.5 seconds, the moon and the earth move fucking 500 fucking miles. All right? Now that's probably going to be minuscule based on the size of the earth, the size of the moon. All right? But logically, think about that. I want you to logically think about that, because here's where I'm going with this. Think about how that would look on Earth. Okay? Think about how that would look on Earth. You probably say that, well, distance plays a big role in this, right? Distance. Okay, I'll agree with you on that. But he goes into this and says 474 kilometers while the beam is headed to the moon, 470 kilometers while the beam is headed back to the Earth. Since the retroreflector sends light back to its original point of origin, and because the returning beam is only 20 kilometers wide when it returns. Now, 20 kilometers wide. How big is that? Okay? 20 kilometers, and that beam comes back, it's fucking 12 miles wide. 12 miles wide, people. When the returning beam is 20 kilometers wide when it returns, then the returning laser beam should miss the telescope that shot the laser beam by at least 928 kilometers. That's another 500 miles, 490 some odd miles, right? This is because both the Earth and the Moon have moved 948 kilometers towards Leo while the laser beam was in the air. But in fact, the laser beam is detected by the same telescope that shot the laser beam in the first place. Okay? With this scenario, the LLR is a type of experiment virtually identical to the two parallel car metaphor. Okay? The line between the Sun and Leo is represented by the path of the two parallel cars. The person in the first car that throws the ball is represented by the telescope that shoots the laser beam. The person in the second car who throws the ball back to the spot on the pavement represents a retroreflector that returns the light back to where it came from, meaning to where the telescope was when the laser was originally fired. The returning laser beam should miss the original telescope by 928 kilometers. I'll come back to this example later in much more detail. Okay. The actual process of doing the LLR experiment begins with an observer finding the retroreflector on the moon. By finding the retroreflector, it is meant that they can detect returning light by the moon from the moon after firing the laser, and detect the light is not noise. I cannot talk about all their challenges, but we'll mention 3 of the problems they face. And here's one of the problems. The most significant problem is image motion, caused by hot and cold cells in the Earth's atmosphere. The hot and cold cells cause the image to weave back and forth and up and down. Secondly, seeing problems are encountered when a point of light on the moon or from a star is blown up or enlarged by either temperature cells or particles in the atmosphere. Now, remember what I had said before in another video where I showed you guys where ESO shot a laser and it hit sodium layers at 90 to 110 kilometers? So I want you to think about that right now. If the European Southern Observatory down in Chile can shoot lasers up into the sky to create artificial stars, and they're hitting a sodium layer at 90 to 110 kilometers, what do you think the fucking moon really is? Ask yourself that. Because based on what he's saying here, he's talking about some sort of temperature cells or particles in the atmosphere. Third, dither problems or jerks in the images caused by the finite mechanical equipment in the telescope drive system. Okay, that's just a small little tremor and micro tremor activity. An observer begins by pointing the telescope as accurately as possible to where the retroreflector is located on the moon. I call this initial pointing of the telescope, whether successful or not, ground zero. Okay? So keep going through this here. Let me see here. Hitting the retroreflector and looking at old light. Now this is interesting. He says, now let's get down to the details. When a telescope is looking at a galaxy 100 million light years away, yeah, okay. It is looking at light that left the galaxy 100 million years ago. It is also looking at where the galaxy was located in the sky, ignoring aberration, etc., 100 million years ago. The same holds true when a telescope is pointing at the moon. All right? Now, this is where this shit gets interesting. And this is where Vivian and I talked about this, and we were laughing at it over lunch on a Sunday afternoon, and it didn't make any sense. But I'm going to see if it makes sense as I read this again. And this guy is saying when an optical telescope is pointed at the moon, because it takes 1.25 seconds from moonlight to get to Earth, the telescope is really looking at where the moon was located 1.25 seconds earlier. Now, that makes sense, right? Because if you're looking at a 2.5 second round trip travel, right? From the time you fire the laser, from the time you look at the moon and a pair of binoculars or a telescope or whatever, what he said before was that the moon and the Earth actually moved. Okay, and when I say the Earth, I'm talking about the whole damn thing. I'm not just talking about. I'm not discussing the fixed plane. I'm talking about the rest of the shit that's out there that's rotating. All right, we're stationary. I'll stick with that. So what he's saying is that you can look at the moon with your eyes right now, but as soon as you put a camera up and you take a picture of it, that fucker traveled 529 miles. 529 miles. So where you thought you saw it, it actually, boom, moved 500 miles in 1.25 seconds. That's what he's saying. Okay? He says here, this means that the telescope is pointed or looking at a spot that is 474 kilometers, about 1.5 seconds, times the average 370 kilometers per second motion towards Leo. 370 kilometers per second. All right? Per second. For all you people in the U.S., you like your standard measurements, 370 kilometers. That's 229 miles a second. Okay? That's 229 miles a second moving towards Leo. All right? Behind where the moon is actually located when the light arrives at the telescope. This is based on the assumption that the Earth and moon are headed nose to nose towards Leo at 370 kilometers per second. In other words, the light the optical telescope is seeing is old light. Now, that's where I started having problems. Because if you can see the moon right now, you go outside, and I'm not looking at it right now, so I'm talking to you guys. If you keep your eyes fixed on the moon, you're seeing this light. So, but as we're all reading this together, does that make any fucking sense? He's saying it's old light. Now this is where Vivian came in and kind of enlightened me, with play on words. And Vivian came up with the idea. He came up with the idea that the moon is actually pulsating. Okay, it's pulsating some light. Okay, fucking mosquito. The moon is actually spinning so fast, okay? I mean, literally like a spinning ball or disc, so fast that it's pulsating. It's pulsating light, and it's pulsating the light at such a high energy level you don't see the pulsations. You can't visualize the light being pulsated like you would say a light bulb when you turn it on and it flickers, okay? You got Luke Francis, who talked about that the moon got its light from being recharged by the sun in the daytime. All right, so we got all these ideas out there that could be possibilities, right? But for right now, we're going to go with the fact that the moon is spinning really fast, and that's how it's giving off its light. It could be a flat disk, it could be a round ball, but it's moving so fast And you're probably thinking, okay, well, why can't you see this? Well, Crow talked about he's been shooting the lunar wave, right? So you got to ask yourself, how are you seeing this wave? Well, um, the moon is oscillating, moving in an elliptical pattern. So it's dropping in and out of some sort of medium. And when it drops out of the zero viscosity medium, and when I say zero viscosity, there's only one fluid out there that offers and delivers zero viscosity, and that is superfluid helium, helium-4, at 0 degrees Kelvin. 0 degrees Kelvin. And I'm going to show you a sample of what that looks like. Okay? I got a virtual online physics experiment simulation I'm going to show you, and what happens when you lower the temperature. Because we all know, John will tell you too, we've both been in the military. When I was out in Saudi Arabia and we were doing ops out there in the desert, dude, it was full moon. But when we laid down prone, to kind of stay hidden, man, the heat from your body would just fucking get sucked out. It just gets really cold during a full moon. Now, you got to think about that. Why the hell is this so fucking cold during a full moon? Because if the moon's giving off that type of light, right, it's got to be in a near 0 Kelvin degree environment where superfluid helium exists. And if it's spinning so fast, that temperature has got to stay consistent. And if it's oscillating and dropping up, it's moving up and down like the way a balloon does at nighttime when it just the temperature drops and the balloon drops maybe about 50, 60,000 feet, and then during the daytime in the heat, the gas expands and it rises back up again. All right. So those are things for us to all consider. All right. So I want to get to the part where he discusses how fast the moon is actually moving. Now, when I say move, I'm not talking about across the sky. We already know it can move fucking 529 miles in 2.5 seconds, okay, or 370 kilometers a second. All right. Let me see if I can. Let me see if I can find this one section here, because they talk about returning laser beam, cosmic microwave background radiation. Okay, so they say the returning beam will miss the telescope by about 948 kilometers. Okay, now here's the problem. Here's where we got to convert this. That 2.5 second journey, round trip, all right? We want to focus on this number. So I'm getting ready to show you, potentially, I'm not going to say for fact, potentially, 948 kilometers is 589 miles, okay? So when let me see here. I'm going through this ether drag. Let me go. Let me see here where we're at. Oh, shit. Hang on for a second. Let me get this shit down. Okay. Trying to find that one section that we had actually discussed with regard to the spinning rotation of the moon. And the calculation we came up with was 827,000 miles an hour, give or take. So if the moon was moving 827,000 miles an hour, you wouldn't notice any other visual surface feature reference of the moon than the same surface features you were looking at. Every time you see the moon, you're looking at the same side because it's spinning really fast, moving 529 miles every 2.5 seconds across the sky at night. So, you know, I'm going to answer questions on that. I know I'm going to get blasted for saying that shit. But this is why I need to talk to that guy who actually drafted this paper, because according to what I'm finding here, and I want to show you guys something. Let's do this. This is the NASA's JPL software program that I want to go through with you guys. John, Vivian, let me know if everybody can see this. Just chime on your mic if you can, please, if you guys are still there. Hello?
Yeah, Robert, we can see everything.
Okay. All right. So here's what I'm going to do. I'm going to give a telescope image. Now, this is the funny thing that I want you guys to see. We're going to do a telescope image. I'm going to zoom in. All right? This is real time, by the way. So here's where Vivian and I are. Let me do this in real time. Okay, slow this shit down a little bit. Okay, so here's where Vivian and I are. We're not in Bogota, we're actually in Medellin. We're a little bit closer. So the image what I'm showing you guys right now is actually the telescope view. So these are where all the telescopes are located on Earth. All right, don't pay attention to this bullshit, because that image is going to change real fucking fast when I get ready to click on one of these fucking telescopes. All right, but where Vivian and I are at, we're actually north of Bogota. All right, we're up in here. But for presentation purposes, I'm gonna click on this bad boy. So I'm giving a telescope view right now. Now you see what just fucking happened? What does this look like to all of you? That looks like a fucking flat, plain surface, doesn't it? Doesn't it? Because it is. All right? So let me speed this up a little bit here. All right, so I speeded this up by 10 seconds. 10 minutes per second. So this is showing the satellites actually flying around the fucking sky. Okay? Can everybody see this? Vivian? John? Can everybody see this in chat? Hello? My
Yeah.
guys still there?
Yeah, I'm not in chat, but yeah, we can see definitely.
Okay. So I want you to look at this. This is the telescope view from the ground. So this is what I've been trying to tell everybody. If you want to keep saying the Earth is flat, you better fucking get it right. I don't know how many fucking times I gotta say that shit. I'm not trying to disrespect anybody either, or offend anybody. I'm not trying to say people are not, smart. And here goes fucking Leo right here. Look at Leo. Here goes the sun. Look at the moon. There goes the moon right there. They're saying the moon is moving 900 and get the fuck back over here. Wait a minute. Hang on. Here goes the moon right here. They're saying the moon can move 948 kilometers in 2.5 fucking seconds away from Leo. There goes Leo right there. Let me pull this shit down. Hang on. So here's your flat Earth. This is Bogota. This is where the telescope is here on ground. So this is 10 minutes per second speed. All right? You got your satellites flying around the fucking sky. All right? They claim they're moving at fucking 17,000 miles an hour. This is just funny. And I know it's just a simulation. But if you notice something, and I want everyone to stick to this model, I'm telling you. You don't have to if you don't want to. But the Earth you're standing on is fucking not moving. It's flat. It's fucking flat. But the atmosphere is above us, the constellations, that shit is rotating. You can see it for yourself right here. This is NASA's eyes on the Earth. This is their software. This is their software. Look how the constellations are moving. This is how it looks to me and Vivian. Okay? This is how it looks to us. Now, if you want to see how it looks to you, we'll come out. I'll come out and show you another fucking telescope view. Let me see if I can get out of this shit. Hang on. Let me see if I can get out of this damn thing. What the hell did I just do? Hang on. Okay. So I got out of that. Let's go back to a telescope view. And let's click, say, let's make it fair. Let's go to fucking Miami. No, fuck it. Let's go where John might be. Kansas. Okay? This is what it looks like in the middle of the United States right now. Now let me tell you what was strange about what I just showed you in Bogota versus what's happening up in the United States in the northern, I wouldn't say hemisphere, but to the north of us. I don't know if you guys noticed it, but let's see, right now it's still moving. It's moving at 2 minutes per second. Let me take it to the 10 minutes a second. Okay, there we go. So as you can see for yourself, Vivian and I see different constellations than the rest of you. Oh shit, what happened? Okay. Vivian and I see different constellations than you guys do up in the United States. We don't see the same thing you do. Now we should. But see, the weird thing about this, looking at this software program, which is literally giving you real time. The Earth is not moving. The ground you're on is not moving. It's flat. There ain't no curvature at all. But these constellations, these fixed constellations, are rotating around us. I showed you that view. I showed it to you. Let's go back to this again. Okay? Processing. Let's go to this. Let me I need to get back to the telescope view. 3D. No, I don't want that. What I'm gonna do here? Get the hell out of that. Take you back to the telescope view. I want to get out of the 3D because it's fucking up my eyes. All right. So if I got anybody over in Europe, let me see here. Let's go to, what do we got here? Want to get anybody in London? Yeah, fuck it. Let's go to London. Let's go to London. Here's London. Booyah. London is seeing the same thing the United States is seeing. And if I'm not mistaken, I think the rotation was different for us. Was it not, Vivian?
Uh,
They got a clockwise rotation, don't they?
yeah, but right now you're facing south, so maybe try to earlier you were facing west. So try to go back to west. On
No,
the
but this.
side, sorry?
So what you saying? Face west.
Yeah, you.
This way?
Yeah, there you go. Go back a little.
Holy shit! Wait a minute. Wait. We got
Right,
something.
there you go. You're facing west now.
Yeah. So it looks like I'm confused on how this rotation's going here, dude.
Well, if you're facing west and you're in supposedly in the north atmosphere, you're gonna see we're pretty much on the equator. So we basically, if we're facing west, we should see like the stars supposedly going straight down, but we don't. It does curve, but we should. Like, we're on the equator.
Man, look at here. Look at here. Look where the moon is, dude. Look where the moon is and look where the
Yeah,
sun.
it
You see that?
yeah, but they're not supposed to move. They're supposed to be like different distances, so they can't move at the same speed. I don't
According
think.
to this is what's happening.
Yeah, no, that's not. It's not.
Oh yeah. According to that, that's what's happening.
Yeah, no, that's bullshit.
It's complete bullshit.
Yeah,
It can't be happening like that.
yeah, that.
Let me
Oh man, watching that ball moving makes my head spin.
Yeah, hang on. Let me get out of that.
But you can go back like on the equator and try to
Yeah,
face.
that's what I'm gonna do right now. I'm gonna do that. I'm gonna go back to the equator.
Because it's one thing to see it on a map, on a CGI representation. It's no one to witness it. And
But wait. Bogota is not on the equator, so we would have to
well,
go to
no,
Paz.
yeah, we're not too far. So well, La Paz is below it.
Well, you know what? Let me try to do this.
Yeah, the thing is there is no.
Ecuador is like right here. So this is the equator right here,
Yeah.
right?
Yeah.
So if I click somewhere in here, there goes the equator. So
Yeah,
let me take it to 10 minutes a second. See what happens. Look at the rotation, dude.
yeah, but you're facing south.
Is this facing south?
Yeah, you can see on
Where? I don't see it on the.
your left up corner.
Oh yeah. I see the compass. Shit.
Yeah.
So where do you want me to face? North?
Well, if you face north, it's supposed to be rotating around the North Star, but you're not supposed to see the North Star from below the equator, which is not true because when I
Okay,
did
so here I am right here. I'm
yeah,
north.
yeah, you see the North Star is supposed to be below.
Dude, this is crazy. Look at this shit. The rotation on the equator facing north is going counterclockwise, dude.
You can.
I'm facing north.
Yeah.
The rotation is
But
going.
you can see. Can you see the North Star? Like it's right on the horizon line on the.
Here.
Yeah, I think that's the North Star. Maybe
Dude,
not.
this is crazy. But look how the stars are rotating counterclockwise, facing north.
Yeah, that's correct. Try to face west or east, either one.
Okay, let me go west. Here we go. West. Everything's going straight down.
Yeah, but it doesn't. It moves like an arc.
Here goes the sun.
Like the sun.
And
You
look at the
know.
moon. Dude, this is crazy, man. So if you're facing west, everything's going straight down.
Yeah, but that's not what we see here. The sun, we can see the sun doing some kind of an arc. Anyway, even when you're on the solstice, like which is supposed to be right on the equator, we can see it doing an arc.
Dude, this is crazy. Look at this, dude. This is weird. I mean, I'm just now playing with this, man, and this is weird, bro. So let me do this. Let me go to Medellin, right?
Yeah.
Let me go to Medellin. And what we'll do, I'll go to Medellin, where we are. And let me see something here. So we're somewhere in here. Hang on. So Bogota's here. We're like here. Medellin's right here, right? So I'll click Medellin right there. And I don't want to face east. I want to face north. So we're in, oops. So we're facing north, and this is what we should be seeing right now. And I can look out the damn window right now. We got a counterclockwise rotation. I can look out the window right now, and I'll tell you here right now, I don't see a goddamn star in the sky.
Yeah, I don't either. It's
I don't
just
see a single star in the sky. I mean, there's a little bit of clouds, but I don't see any stars.
let me see if I can see the moon. Hang on.
Dude, this is crazy. So I want everyone to be convinced. This is here's your flat Earth, your constellation, everything above you are rotating. Clockwise, counterclockwise, or going straight up and down. Everything's rotating over your head and around and down.
Yeah, I can see nothing, Robert. No moon.
Yeah, that's what I've been trying to tell people.
And I don't.
You've been here 4 years. You've been here 6.
Yeah. Hi, it doesn't show
We don't
anyone.
see this. We don't see any of this. We don't see any of
But
it.
it obviously moves a lot slower, so we'll
Oh
have
yeah,
to
it moves a lot slower. I can
watch
put it into real time. Here we go.
compare it. But
Here's real time right now. Real time. This is real time. The clock, everyone sees it. It's August 29th. It's 9:28. Well, that's the wrong time because that's my computer time. But it's 8:29 p.m. And Vivian and I are in the same city, not too far away from each other, and we do not see this at all. And this is facing north. I can see clear north. Can't you, Vivian?
yeah, I can see north pretty clearly. Well, I can hardly see stars, but
Can you make out Ursa Minor? Can you make out Draco? Can you make out
no, no.
Cassiopeia?
Oh, no, yeah, I can't. No, well, the problem here is we have the mountain. Maybe the mountains are
Because
blocking the
directly
view.
above us, they claim his was supposed to be directly above us. Let me see if I can even find the moon, dude. Is the moon supposed to be out?
Well, it was out earlier in the States when you were on the northern atmosphere, but
Yeah, in the States you can, but it's not here. The moon's not even here. The moon is not even.
so
Oh, dude.
so you can see at night time you can see in the well, hang on. But it was along going along with the sun, so
Yeah, it's crazy, dude.
basically, yeah, the moon. Can't you see?
Let's do this. See if we can pick another city. What do you think it would be like in Anchorage? Wait a fucking minute, dude. Is it fucking China? What the fuck is China doing up there? Well, that's weird. Let's see what we can see in Anchorage.
They're supposed to see if they can see the sun, they have the moon supposedly right now. So
And this is 2 minutes per second.
yeah.
Yeah, this is a fantastic tool, dude. It gives you so much perspective, you know.
Yeah,
I want to look north on this.
I used to have an app on my phone.
Here's north.
But there's a few you can look to learn the constellation. I used to play with it a little bit for a while, but the thing is, that doesn't mean like we're spinning. It means that what we see is rotating, but it doesn't mean
Well,
we are
yeah,
spinning.
we're not spinning, but what's above us is.
Yeah, and
And I think that all of this shit, all these satellites, all of this is moving with the rest of this up there.
yeah, those satellites, they're not. That's not.
No, well, depending on what the speed of this is. I mean, if we were to do this, say, speed it all the way up to say maybe 35 minutes a second, look what it looks like. It's fucking crazy, dude. You know what, let me screw around with the elevation, dude. What did I do with the elevation? Oh, 90-degree elevation. Look what happens at 90 degrees. So when you look up in the sky and you see the time lapse, this is what you see.
Yeah, because you're in the southern atmosphere. Where are you right now?
This is Anchorage, Alaska.
Okay, yeah. So you
But let's go down to Chile.
you can see the North Star pretty well. Okay.
Yeah, let's go to Chile. Hold on.
And let's see if I see the Southern Star.
Let's go to Chile.
Or Buenos Aires, even further south.
Buenos Aires.
Yeah, as further south as you can, and face south.
And face out.
There you go.
Okay, so I go to 90 degrees. Elevation. This is what it's supposed to look like. Let me speed this shit up. Let me see what happens. So this is what it's supposed to look like. Buenos Aires.
Yeah.
Now you look at the time down here. You go through the whole night. This is interesting, dude.
Try go back to 0-degree elevation, just to.
Okay.
Let's see.
Okay.
And maybe slow down the speed a little bit, maybe just like 10 meters per second.
Okay.
Just to see if we.
10. There you go.
Yeah, around it.
Now this is more of a clockwise rotation.
Yeah, which. Try to face south. You're not facing exactly south. Try to face south to see.
Okay.
Yeah, you go. That's what I want to see. And try to elevate a little bit, maybe like 30 degrees or something.
30 degrees, okay.
Yeah, around that.
30 degrees. There you go. Clockwise.
Uh-huh.
But further north for you and I was counterclockwise.
Yeah. Yeah, because you,
I mean, how is that possible?
well, if you're facing south,
Dude, I'd love to do a side-by-side with this,
you can
where
do
I
that.
could show 4 different locations and what's going on with the sky.
Yeah, you
I'm gonna
can.
work on that. I'm gonna work on doing a side-by-side where I can see what's going on with the fucking sky, bro.
Okay.
Because this just doesn't look right. Stop that bad boy.
Well, the basic fact, there's no parallax whatsoever.
No,
For thousands of years, just, you know,
no,
like
no, not at all.
it proves that this is moving around us and that we're not moving.
Everything's moving around us. We're not moving.
Oh yeah, no, we're not moving at all.
Yeah,
I'm
we're
not
not moving.
doing it. I'm not moving right now. I can tell you.
Yeah, and this is courtesy of NASA.
We're not spinning. You know.
See, they want everybody to believe this. They want everyone to believe this. You see how this is rotating?
Oh yeah.
This is what they want everyone to believe. But what's really happening, okay? What's really happening is this. You're on the ground. Everything else is moving around you. You're not moving. That's what it comes down to. That's what it comes down to.
Mm-hmm.
So yeah, we've been doing this for a little bit, and I just wanted to show that to everybody. Want to answer some questions for some people. I'm gonna put some links in the chat for people, so they can check this stuff out. That's the lunar laser ranging. If you want to get that, you guys get that that NASA animation. It's called Eyes on the Earth. Anybody want to ask any questions? What are people saying in chat? Did John leave? Or is he still in here?
Yeah, he is.
Where is he?
He's here.
Your camera's on, dude.
I'm still here.
Your camera's on, brother.
Sorry.
Chime in, man. What do you think? Man, tell me you didn't go to sleep, dude.
No, I didn't go to sleep. It's all baloney, man. That whole paper was baloney. I almost went to sleep reading that
I
paper.
was looking through it today when we had talked about it too, man. And I was looking at the guy's background, and yeah.
Well, I didn't have to. I don't even know the guy. I don't really care about his background. I just looked at the substance of what he was saying, and it's preposterous.
Yeah, he never got to the meat of what the hell is really. I mean, I still gotta go through. I mean, we're gonna do several other hangouts where we're gonna look at those university observatories lunar laser ranging research papers, because what you had shared with me with regard to how the power of that laser, there's no way it's traveling 258,000 miles.
No, it's even worse for lasers because the free space path loss with those, like we were talking about, is
Yeah.
even higher than the longer wavelength radio.
Yeah. Yeah.
So you're talking serious wattage to even get there. That's just a half a trip. That's just to the moon.
That's
How's it getting back? I got another question too. How do they differentiate between photons coming from other sources back?
Yeah.
Frequency. So that's supposed to be the frequency, the ones they fired, and the one they're reading back, they taking into consideration. It's like when the light travels in a fiber optic, every 100, 200 miles or so, they have to repackage basically the light, and because it goes out of sync, out of wave, and that's basically how they can calculate. But I don't know, it's bullshit. The thing is, a laser going through the atmosphere would already hit so much refraction. Doesn't matter if it's 4,000 feet high. That's not. There's so much refraction. It will not make it to the moon. There's no way. Light will be refracted everywhere. And maybe eventually, if they could recondense the light from a telescope and reshoot it halfway through, and maybe having like 2 or 3 telescopes, basically channeling the laser, maybe eventually that would be doable. But
Yeah, when they describe the retroreflector and the size of it, and they're saying that they have to shoot this laser at this thing, and by the time it gets there, the beam is so wide that maybe they hope they can hit it, and the light will come back. But what this guy is saying is that the moon is moving 948 kilometers in 2.5 seconds. And no, and a 1.25 second. It moved 529 miles in 1.25 second. There's no way it's 258,000 miles. It's closer.
well,
I know that we wanted to talk about what the speed of the moon was, and yeah, we did discuss that. This
Yeah.
guy saying is moving. It's old light, just like with stars. They're saying that the stars that you see, if they're saying they're 1,000,000 light years away, they said that by the time you traveled 1,000,000 light years, by the time you got there, that star wouldn't even be there.
but
This makes no sense to me at all.
they have to say that because supposedly the light travels at 300,000 kilometers per second. So they have to come up with those numbers, which already just by the time the sunlight reaches the Earth, which is supposed to be like around 8 minutes, I think, what they say, is obviously not. But the distances, you cannot comprehend it, you know. It's not, at least many people that can comprehend the distances. So they have to go to turn it into light years, and then it gets even, you know, we're talking 6 trillion miles every time we're talking light years. So it just, you cannot comprehend those distances. So what I'm getting at is basically they're talking about old light because this has to match the numbers they got for the speed of light, which doesn't have to be that fast. The light doesn't have to travel that fast and that further. You told me you saw that video when they shot through a bottle of water. They shot through light and they recorded at a super high speed camera. We're talking like hundreds of thousands of frames per, I think it was 2 million frames per second, something like ridiculous. And you can see the light slowly going through the bottle. So obviously it behaves as particle in that way, but it's So that doesn't match your observation. Like light does not. And how would light travel in free space?
Exactly. Well, that's interesting you say that, Vivian, because as I was looking through that document, John and I looked through and I shared it with you, I stumbled across some collateral data discussing superluminal signals. Okay?
Superluminal, okay.
And because I couldn't wrap my head around what they were doing and how they were trying to explain what they were doing with those lasers. And this paper here, superluminal signals, all right, they talk about faster than light velocities. Now, I'm not going to go through this paper now in this hangout. We'll do this week. We'll probably do it maybe, if not tomorrow, we'll do it Wednesday. We'll talk about this. I'm going to share this with you and John.
Okay.
Okay. But what they discuss here, they basically shit all over Einstein's theory, relativity, when it comes to the speed of light. The speed of light is not a constant at all.
Yeah, no.
What they discuss in this paper blows that out of the water. Blows it out of the water. Those times and speeds and distances, okay? When you talk about superluminal signals, you're literally discussing things moving faster than 2.5 seconds. You're looking at something moving faster than 948 kilometers in 2.5 seconds.
Mm-hmm.
And this falls in line with John and I talked about very early on when we first met, when they talk about quantum mechanics, electromagnetic wave propagation. John, did I not just write a fucking paper about this?
Yep.
Where I talked about electromagnetic wave propagation? That's what I just did for a research paper. Is he still there?
Yeah, I'm still here.
Okay. So we're gonna go over this. We're gonna talk about this. This will be for another hangout, because this might explain what might be going on with what they're trying to do with lasers and what they're trying to discuss at CERN. Because CERN is actually looking into superluminal signals. CERN. Now, here's the thing. That topic alone in quantum mechanics, you put them together, there are papers out there talking about teleportation, time travel, and screwing around with time.
Oh, yeah.
And, before we started the show, I saw people chatting out there talking about how, people were discussing how they think that, maybe they're screwing around with time to get people to forget things or to think about certain things. And when you talk about that particle, it's the Large Hadron Collider at CERN. And the amount of power and speeds that are required for them to do what they need to do. This is not a single-use device they're using. This is a multi-use. This is a dual-use purpose device. And you come up with all types of new discoveries when you think, okay, holy shit, we could use it for this. We could use it for that. I mean, when I did that little teaser video with that movie Deja Vu, where they talked about the NRO screwing around with adaptive optics and being able to look back 4 days into the past. Well, if you can look back into the past, that means you can look forward as well.
Well, supposedly...
Superluminal signal propagation and transport.
Yeah, but you can't physically manipulate time, dude.
No. I'm not saying you can physically manipulate time, but what Robert Shortman and I talk about when we were on his show, and he brought up those patents on how they could actually manipulate your consciousness using electromagnetic wave propagation.
I was doing that back in the 70s.
Yeah. That's how old the patent was. And they're doing it. I mean, they're using Wi-Fi to do it today.
I wasn't using Wi-Fi.
They can change your consciousness through electromagnetic wave propagation.
Okay. Yeah, because our brain have electromagnetic.
Yeah. You emit specific frequencies.
Yeah. Oh no, yeah, they know about that, of course. Yeah,
and your heart actually generates a higher level of electromagnetic energy and wave propagation than your brain does.
Mm-hmm.
You give off a broader signal through your heart than your brain. So superluminal signal transport and quantum mechanics electromagnetic wave propagation is going to be the next discussion we're going to have. And that's going to tie into what is going on at CERN. Because if they are screwing, not that they're not screwing with time, but if they can look backwards and forwards, how far forwards? Doesn't matter how far back. How far forward can they see?
Remember what I told you about CERN when you called me the other night, and I said basically that well, I know you don't believe in that. I don't really either, but that little conspiracy that has come out for the last year about the Mandela effect, and that's just last year when they start to crank up CERN, and I'm saying, okay, doesn't have to be, but what if those are linked? What if they, I'm not saying they are affecting or changing anything in the past, but what if they are able to observe, and maybe in a very small way, interact or change, you know, what would be the repercussions? What would be the, you know?
Exactly. And John's right.
I would explain, you could explain the Mandela effect just by the fact that they are playing up with CERN, and I think I don't think it's a Hadron Collider. I think that's bullshit.
John's right. You can't manipulate time, but could you influence a specific event?
Yeah, you can't. You're not supposed to, obviously.
Yeah, well, I mean, that's why what the conversation John and I talked about with regard to the delayed choice quantum eraser experiment and the double slit experiment plays into everything that we're going to keep talking about, is that if through just simple observation, something just changes its behavior. If CERN is using superluminal signal transport, faster than speed of light type of whatever they're doing, and they can observe this. Say they can observe it for maybe 5, 10, 15 seconds, 20 seconds, right? Because what they're claiming, when I've read some of the research papers that CERN's put out, and they're only able to observe these particle collider experiments for maybe less than a second. They can only capture it for less than a second. So they're trying to increase their capability to have a longer view at these type of events.
Yeah.
So if they've already had the capability to look at a future event for, say, maybe a second or two, or maybe 5 seconds, just observing it, if you pair that up with what John and I talked about and that show we did on the delayed choice quantum experiment and what's happening to the photon as it travels one path, and if it hits that one path, you know exactly where it's going to end up. That means just simple observation is affecting the future.
Oh yeah, absolutely.
They don't have to go back in the past. They're saying, okay, we already know what happened.
Well, that's the thing with the double slit.
Can we put these events together, and we just need 2 seconds? We need 2.5 seconds.
That's it.
Everything is 2. Remember, you have amateur radio operators who are saying that they can bounce a signal off the moon 2.5 seconds. You got observatories saying it takes them 2.5 seconds for a laser to come back to tell them laser range the moon. They're all laser ranging the moon, but they never want to fucking tell you how far it is. Somehow the moon it's always a 2.5 second fucking return. It's never been 3 seconds. It's never been 1.5 seconds. It's never been a half a second. I mean, give me a break. You're telling me you're going to have that constant measurement every time you laser range it? No.
No, I don't think it's 2.5. I think it changes. It has to change. I don't think that paper gave. I don't think they gave exact microsecond numbers. It could be more accurate.
They've included picoseconds in one document we read. Yeah. But we found out when you calculate the picosecond is nothing but it comes out to be 2.5 seconds. So it's either happening in a picosecond or it's happening in a real second.
Yeah.
Standard second. So what the document John and I read says they were measuring everything in picoseconds. A tenth, 1/10 to 1/100th of a second.
Yeah, which makes the moon a lot closer.
Which makes the moon a lot closer. A lot closer.
Well, but that's the thing is, however they're supposed to be able to measure the distance of the moon, even if they can, even if the moon is closer, it doesn't say anything about the nature of the moon. That it says basically, and that's the thing about people believing that those reflectors are on the moon, is like it's a hard element which you can either lens or drop something on or bounce light against. And that we don't know. We don't know. But when we look at the moon during the day, if it's out on the day, we can see the blue sky through it. Let's put it that way. And when it's nighttime, we can see it black. That would mean that the moon might not be a hard object. That's the basis.
It might not be a hard object.
It might not be a hard object. And if it's not, then that comes back to that video I sent you. And they're starting to do those holograms by projecting laser beams at high frequency into a plasma gas. And well, what if you're projecting something into a helium-4, into a superfluid matter? How would the light behave then in that environment? If it doesn't, is there zero viscosity, zero refraction?
Yeah, that's interesting you say that, because that one experiment I showed, I did a side-by-side video where the University of Maryland actually, they contained superfluid helium. They put in some frozen particles.
And it goes up.
And they shot a laser inside, and the laser was bouncing off of all the particles. You could see all the particles moving.
Mm-hmm.
You could see waves of the particles being created.
It would reflect like...
Yeah, but the waves you were seeing was not because of them moving through the fluid. They just wanted to show the quantum vortices. Now, here's something interesting that I'm going to pull up right now that I wanted everyone to see. And let me break this down here. This is quantum chemistry. Let me see here. Quantum interference. Physics. See if I can change this thing here. Okay, here it is. I got it. Let me pull this bad boy up here for everyone to see this. And again, this is, you know, I couldn't find the experiment so I could make it helium, but we can kind of put things together to figure this out. This experiment is called States of Matter Basics, and let me pull this up here. So we got neon, we got argon, we got oxygen, we got water. So I'm going to do O2. I want to change the state to a liquid, right? So get this. Right now, this is water. Okay? At 69 degrees Kelvin. Can everybody see this?
Yeah, we can.
All right. John, what's normal atmospheric pressure? What's Earth's normal atmospheric pressure?
I think it's 14, like 14 something pounds per square inch.
14 pounds per square inch? Okay.
Somewhere around there, I can't remember on the pounds per square inch. Can you do tours?
No. It's supposed to be 1 bar, isn't it? It's 14.69.
Yeah, so, yeah.
Pound per square inch.
Okay, so let's do this. I'm going to bring the temperature down. Right? 5 Kelvin, 4 Kelvin, 3 Kelvin, 2 Kelvin. Keep looking at the water molecules. Zero degrees Kelvin. Ain't nothing fucking moving, man. So when we look at the chart over here, okay, nothing's moving at 0 degrees Kelvin because it's pretty much fucking frozen. all right? But if I increase the pressure, right, the temperature goes back up. And it keeps going. But if I drop the temperature back to 0 degrees Kelvin,
it will slow the pressure down. There you go.
okay, the pressure is stable. What is that? 124 or 125.
That's should be Pascal, isn't it?
Yeah. But if I increase the pressure a little bit more, right, it goes back up. Now, supposedly the pressure increases as you get higher in altitude, right? Right?
Barometric
No.
pressure, no, it decreases.
The pressure decreases?
Yeah, decrease and the temperature goes down. That's
Until you get so high, then the temperature goes up.
Okay, so if I keep lowering the temperature, go back down to 0 degrees Kelvin. Okay, say I'll increase the pressure a little bit more. If I keep increasing the pressure, right, what ends up happening is that the temperature of the water, oh, that's fucking neon, I'm sorry. No, I want to go to water. Hang on. Let me lower the temperature. Get it way down. So what's the temperature, let's say, in the stratosphere? It's under 50 Kelvin, right? Right?
Say again?
What's the temperature in the stratosphere? I mean, like, say, thermosphere.
Hold on a second.
Give me Kelvin.
26.6 Fahrenheit in the stratosphere.
So what is that in Kelvin?
270. Sorry.
270?
Yeah.
Really?
Yeah.
And the pressure? Oh, you said it's 270, right?
Oh yeah, it's 270.
Yeah, I dropped it too much.
There you go, almost. But that's the thing. I don't think helium behaves the same way as water does. I think it behaves the exact opposite.
Too.
So the lower the pressure, the cooler it gets. No, sorry, the higher the pressure, the cooler it gets. So if you get high pressure in the stratosphere, then it will be really hot with water, but it will be really, really cold with helium. 270. There you go.
270.
Yeah, you're 270 Kelvin now.
So, but here's the deal. Ah, look at this. It went critical. And that's for O2. Now, I wanted to do that because we all know that they're using what? Liquid O2 to fire rockets up into the atmosphere, right?
Yeah.
So how the fuck do they get the rocket from not fucking exploding like this just did? Think about that.
How come the Earth doesn't explode?
Because they got liquid nitrogen on board as well. The nitrogen is stabilizing this reaction.
Yeah, yeah.
To keep it from blowing up. But if that nitrogen doesn't somehow, some sort of equilibrium state is being created, you're going to have more nitrogen on board than you have liquid O2. Because last I checked, what, liquid nitrogen wasn't combustible, right? I can't change the rest of these damn.
In the liquid form, no, but in the low pressure, but yeah, you can burn that hydrogen. That's why if you extract the hydrogen from the water and you are, let's say, 1 bar pressure, atmospheric pressure, then it will blow up. But hydrogen is very unstable. That's why we don't have car running on hydrogen, because it's not stable enough.
Yeah.
You can mix it, and it makes. What we do is, if you want to improve the range, the miles per gallon of your engine, your combustible engine, you mix it with hydrogen instantaneously, and you get a much better combustion, and you're up to 90% burning, which is about 3 times what your basic engine will burn, about 30% of the gas. So, but that's because you're going to mix it with oxygen. But on its own, it's not stable. On its own, basically it's a bomb. Under high pressure, it's a nitrogen bomb. That's how they make hydrogen bomb. It's high pressure.
Yeah, it is. It basically becomes a nitrogen bomb. Exactly. Yeah. Exactly.
It's stable at low pressure, at atmospheric pressure. It's fine, you know. But going back to
I just don't see how, you know, when you throw in all that velocity, you throw in all that pressure, you throw in all that acceleration, you got all these gases on board. You know, I heard one NASA astronaut talking about how rocket science is, I mean, literally, getting into space is highly complex and really dangerous. I mean, they keep emphasizing that. They keep.
Yeah, and if a rocket has to push against something to create lift, then obviously in free space they say it's because of the shape of the nozzle. It's pushing against itself, and that's how they say rocket works very well in space. That's the excuse they're coming up with.
Yeah.
But in a vacuum, in a perfect vacuum.
What vacuum?
It will suck anything out of that rocket.
Yeah, absolutely.
So
absolutely. All right. So
number one, there is no vacuum. Number 2, if there was, you ain't getting any propulsion.
No.
Yeah, you can't.
Yeah, but you know what? You'll have people all day long argue that whole thing on how rockets work in a vacuum, but they never tested one. They never tested full-size rockets.
Yeah, they did. Did you see Did you see it on? I think I seen a YouTube video. Guess what they had? My question is space in a container? 6 inches wide.
Yeah. So they're doing everything in a closed, controlled environment. And they're saying, well, if it works like this, it's got to work when we get it outside.
Well, when they released the pressure, I don't know what the rocket had in it. I just seen the video. But as soon as you do that in an enclosed container, well, that gas then fills that container, right? You no longer have a vacuum.
Yeah.
So the whole thing's a straw man on nuclear steroids. It's stupid.
Yeah, no, you can't. You can taste it anyway. There's no way you can taste it because in closed environment, then you'll have walls, and eventually you're not gonna have a perfect vacuum anyway. So
well, you could probably do it. You could go up to Cleveland in that big vacuum chamber, and then get a really small like CO2 cylinder. You could try it then.
And see what happens.
Yeah, right.
But it won't. Yeah, it will not push against anything. That's the thing. There's no way. Even if you put a nozzle on that little, it won't.
Yeah, it doesn't matter. Nozzle ain't
how
gonna
much pressure you have.
Yeah, it ain't gonna matter. It's not pushing on anything. It's over.
There you go.
Yeah.
But going back to the moon, I want to know what John.
Yeah, I swear to God, man, I'm so focused on this moon thing, man.
Yeah, because you know, people try to come up with.
I want to make a call to two of these observatories, and there's some specific questions that John and I are going to have for them. Because one, we want to know the power of the laser. Number two, we don't want all of this back talk and this double talk bullshit about 948 kilometers movement from the constellation Leo. Now we see where Leo is and how close it is to where the moon is at. You're going to tell me the moon is somehow in 2.5 seconds moved 529 miles? I'm just going to ask him direct. Okay, let's do this. Answer just a direct question for us. When's the last time you lasered the moon, and how far is it really? Can you show us the data? Don't tell me it's 258,000 miles. Show me the data. And don't tell me it's going to take a week to get it to me. Point me to the link of where I can download it right now. Because Robert Shortman and I actually downloaded the information where they actually decipher and they describe to you how to read the actual numerical data. And we're working, now that we know, how fast a picosecond is, now I'm going to start, I've got a MATLAB program where I'm going to punch those numbers in, and they literally lasered the moon probably, 100 times in 2 weeks back in the late 80s and 90s. And all that data is just nothing but fucking numbers that don't look like anything, man. They just look like scrambled, cryptographic, generated, numbers that were created from some number generator. But I'm going to break down a few of them, and that should do it. That literally should do it. But John and I want to actually talk to one of these observatories who are listed online, who actually do this. This is all they do. And, I'm trying to get one of the people to actually return the phone call right now. If they return the phone call, I'm going to get them literally, I'm going to try to get them on live.
Let me ask John this. Remember when I asked you, Robert, what would happen if you videotape the moon with a high-speed camera?
Yeah, you and I talked about this, Vivian.
Because what will happen, like if the moon is not, I mean, what they say it is, and it's maybe eventually a projection, then you're gonna start to see flickering. And if you see it flickering with a high-speed camera, then that would mean, well, we can go.
I got those links for you too, Vivian. I'm gonna shoot them to you tomorrow. Yeah. I found a company that sells a camera.
Yeah, I saw them. Yeah,
but get this, 25,000 frames per second, man. We could, and they've got an infrared capability you can attach to it. We could put this thing outdoors one night and just let it run.
Let's do it.
Let it run for like an hour.
I think you have an hour.
No, you didn't even have an hour. I said 30 minutes.
I think you have a few minutes with those cameras.
Yeah, I think we can get them up in 15, 20 minutes of footage, and then we just post it. Yeah, 25,000 frames per second, dude. That's.
We'll need a full moon, a clear sky, if you want to do it here, which is easy to get. But
yeah, we could go to the top of Las Palmas. You know where we could go.
Oh yeah. Oh yeah, I know.
Yeah, where everybody sees where everybody can view the whole city up at Las Palmas with Tesoro. Yeah. We can go up to Tesoro. We go up there. We shoot. We take the camera up there and we shoot it. Boom, 15, 20 minutes, and we post it.
But hang on, the moon will have to be on the other side of the mountain, because if you go on that side, the moon is going to come up behind you. If we're going to do it on a early night.
Then we'll go all the way up to as high as where remember the Texaco gas station is at? That's the best place to shoot it. We'd be able to get it right there.
Okay. Yeah. Well, we can work something out if you get the camera, but
I can get the camera.
Maybe it has been done. I'm going to look for it.
No, nobody's ever did it. I've been looking for it online. No one's ever did it.
All right.
No one's ever took a camera that can shoot 25,000 frames per second and pointed it at the moon. Nobody did. No one's done it.
Well, it ain't reflecting light anyway. It can't. Not if it's a sphere. It can't.
No, we're not saying it's reflecting light, but what Vivian is saying is that it's spinning so fast that it
The
just
source of it.
friction, maybe the friction alone is causing it to glow. Like if you get something spinning real fast, like I've seen videos where they put some type of sphere inside an electromagnetic field, and it just spins so fast that it gets white hot. So that's probably what the moon is doing. That it's spinning so fast it's
Are
white
you
hot.
saying the moon's spinning fast?
Yeah,
Well,
I mean, literally spinning. That's what I brought up earlier. That the potential reason why people are actually seeing the same surface features is not because it's just fixed, but it's spinning so fast you can't see how fast it's actually spinning, especially if it's close. We're talking about hundreds of thousands of miles an hour.
or if it doesn't spin fast, but it flickers and it's been projected, then that would mean we could break down the frequency. In that video I showed you, you can clearly see the laser flickering, but you can see a 3D picture suspended into the air. And in order to control the length, the wavelength of the light, you have to have it flicker at such high frequency. Can you try to prove the video, Robert? See what John thinks of it, because that could be one. Because many people are saying, yeah, the moon is a hologram. Well, but try to back that up with some proof. And if it's a hologram, well, a high-speed camera will show it because it's going to show it flickering. If it's a hard object, then it could be something spinning so fast.
Yeah, and that's what I also want to address. I want to get a bunch of videos put together, but I'm free. I don't want to get no copyright strikes.
Yeah, no.
I don't want to get no, because these days everybody's trying to
But
protect.
anyway, let me see. Well, if you type in laser hologram, you're going to see a few of those. Laser hologram, and you're going to see how they're able to. It's pretty bulky technology because they unveiling it nowadays.
Oh, the laser hologram projector?
Yeah. And you're going to see
the 3D laser one that you gave me.
Yeah, for instance, yeah, you can see it flickering because it's pretty bulky, but you can see a 3D shape suspended, and it doesn't use its mirrors or anything like any other holograms or projecting into glass or into fog or whatever. It's suspended.
Yeah, I don't want to play this. You don't get a strike.
Yeah, no, don't. But if people want to see what I'm talking about, it's just type in YouTube or whatever. Type in.
I'm gonna put it in the chat for everybody to see, so everyone can get kind of a visual of what these holograms, what they can do with hologram technology.
And that's human nowadays technology. It's something very, very basic. But if the moon is a hologram and it's cold also, then it could be it. But then the high-speed camera will show it flickering.
Yeah, that's true.
So, and that could explain the lunar wave also. When you have it, it could explain a wave. I don't know how to put.
Yeah, I want everybody to see this. But see, here's the thing: what we're trying to do here is that we're talking about current technology. I mean, we also got to discuss on how this was potentially done, hundreds of years ago. How were people able to see what they're seeing? There had to have been something out there, or there has to be something else out there that could be potentially has been creating what it is we've been seeing for hundreds of years, maybe a couple of thousand years. And I know where John wants to go with this right now.
Yeah, go to Genesis 1.
Yeah.
And then just read right down the page right there. You'll come to it.
The lesser light to rule the night, and but it's a light.
Yeah, I know that. John wants to go down that road on that one.
I'm with you, John. I'm with you on that one.
Oh my God, another
Tell him again, Vivian.
Judas.
Another
Judas escape.
The other day I asked him at the restaurant, I say, hey, do you
No,
believe
no,
in
you did.
yeah,
You did,
so
Jared.
I asked you,
I know.
and
I did, and I told you too. I said John's gonna love you when you say that. That's what
Tell him again, Vivian.
I
well,
told you. Yeah.
it's really, really hard to, when you know what we know, it's hard to go against it. But it doesn't mean it's whole truth. It means like, well, what else
Yeah, I know.
is in
I
that
know.
book
I
that
know.
can help us to see? You know, I'm not pushing it
It's
on you
okay.
anyway. That's not
That's all right, guys. That's all right. That's all right.
my.
That's all right. All right, listen, fellas. Let's probably do this again on Wednesday. Maybe we can do it a little bit earlier for people. So you guys let me know. I want to do this a little bit earlier for them. I got to give the little one a bath right now. It's late for him. But on Wednesday we're going to talk about. I got two documents to share with you guys. One of them is called "Is it possible for superluminal signal velocity without what's the title of the document? Without violating causality." John will love that one.
But that reminds me of quantum communication, and
Yeah, and that's what this involves: quantum communication. The
they
other one,
split two atoms, and when one is behaving in such on one side, the other one just basically replicate
yeah,
what the first one does.
Yeah,
that's
you're
exactly what
talking
we're
about
going to discuss.
entanglement and non-locality.
Uh-huh.
Yeah, that's what we're going to discuss. That's what these two documents. I got one that talks about superluminal signals and engineering perspective. Another one's titled superluminal tunneling. So I've got three documents I'm going to share with you guys. We'll talk about this on Wednesday, um, and that should be an interesting chat as well. I want to bring this one to a close. I want to appreciate everybody that's out there. I know we kind of went in a few directions here. Um, we discussed the potential speed of the moon. I'm not saying that is the speed. That's why I put a question mark at the end of the title of the hangout. We're still looking into this. We got to have some conversations with a few people. I definitely am waiting for an email from the guy who actually drafted that paper, and I want to ask him a little bit more detail where he came up with a lot of this information. But again, if they're shooting lasers at the moon, it's not 258,000 miles hitting a fucking something the size of a suitcase. Okay? Now let's get that straight. You guys saw that NASA illustration I showed you from their software program. When you get down to observatory Earth view, you're looking at the Earth from a distance. It looks like a ball rotating. And then when you click on that one of the observatories or anywhere else on that map, it takes you down to a ground level view and you see the constellations actually rotating. So the upper layers of the atmosphere are moving. The ground you walk on, stand on, sleep on, drive on, live on is stationary. Period. You saw it for yourself. That's fucking NASA. You got anybody out there who's listening right now and you want to believe the Earth is a fucking spinning ball, you go to that fucking website. Go to NASA's website. See it for yourself.
Let
And
me
ask them. Don't question me. Don't send me private emails telling me I'm a fucking idiot and I'm stupid. Or you don't like that I curse. If you don't like that I curse, fuck you.
Robert,
I don't know who you are. I ain't got no problem with you.
can I just comment quickly on that?
Go
Just
ahead.
when we touch on that app from NASA, the reason I say we're stationary and the stars are moving around us is because stars are not at the same distances. Some are trillions of light years away, and some billions and hundreds of stars. So you
Wait.
should see parallax. Those stars cannot move all of them at the same speed, and that's why I can
Okay.
see why we're not moving. Stars are moving, we are not. Because if we were moving, the stars in the foreground would move a lot faster than the ones in the background, meaning
Exactly.
further away.
Exactly.
If you cannot
Exactly.
see that, if you cannot comprehend that, well, I can comprehend because I design and I use 3D every day, all the time. And I can see how when you move something in the background, it's always going to move a lot slower. And that's what you should be able to observe on the stars. So it's not so much about the orientation or direction they take, but how you should see some kind of parallax between them. And you never, ever see that. And you have never, ever seen that as far back we can go. So that I just wanted to to clarify
Yeah,
that.
and that's the clarification. Everyone out there who wants to talk about the Earth being flat, be specific, people. I can't stress this enough. Don't, I mean, if you've been putting out videos and you've been talking about, yeah, the Earth is flat, the Earth is flat, you know, and you keep addressing the same thing, you got to be specific and tell people, hey, listen, you know, I got this software program that, you know, Robert BASSANO was talking about. It's developed by NASA. When you get to ground level view, the Earth is stationary and flat. But up above us, there's some things going on that's moving around us. We're not moving. And the problem with people who are putting out their videos, they're putting out good information, but they don't want to come out and admit the construct, design, and shape of the Earth. They don't want to say it. They just want to say that, oh, it's just a fucking flat fucking pancake. The whole fucking Earth ain't a flat fucking pancake. The ground you walk on is, but everything else is moving around you. There, because then we all get taken much more seriously, because now we're getting down to a real plausible, viable design and construct of where we're at, where we're going, what we're doing, how it's all working. But if you're gonna keep saying that fucking Earth is flat as a fucking piece of paper, the whole damn thing, all the atmospheres, then no one's gonna believe you. No one's gonna take you serious. You saw it for yourself when I showed you in the illustration. That's NASA. That's not Robert BASSANO. That's not John. That's not Vivian. That's 3D imaging software that they developed to show you, hey, this is where you're at. They ain't never going to come out and tell you, yeah, the Earth is flat. Because they fucking know the whole fucking Earth ain't flat. The ground you walk on is. Put that out there. Get taken seriously. So that we start getting down to some real data, some real research. Answering some real hypotheses, developing some real variables.
Now, preach it.
Coming up with some serious fucking conclusions, rather than, oh well, the boats are going over the horizon and you can't see past this distance. Man, fuck all that shit. Start looking into the information. Because John and I have been looking at that one document probably for about a week, John, 2 weeks, and we just figured out today, fuck, everything that guy was saying, that shit can't be taken seriously. And we were focused on that. But we came out tonight to let you guys know that, hey, listen, a lot of what this guy is saying, this shit may not be right, because if the moon and the sun is really moving 948 kilometers in 2.5 seconds, holy shit, it definitely ain't as far as what they say it is. And I said this a long time ago. I saw the moon one night and went to the bathroom. It couldn't have been more than 3 minutes. And the moon was gone. So it's definitely moving really fast. Now, is it spinning like some damn top real fast? I don't know. Vivian and I are definitely going to do that experiment. I'm going to get that high-speed camera. We're going to go up to the top of the city of Medellin and wait at a time when we know we can get a really good, clear sky and a full moon. And in 30 minutes, we're going to post the damn video, man, so that everyone can see it for themselves. If the moon is flickering or what the hell it may be doing or how fast it may be moving. But we're going to do this. All right? So anyone else got any information they want to share, you guys, you can go to my About page, click on, send me an email, send me any information you want. I got a lot of information I actually want to share from viewers, people who are actually looking at my videos and you know, really giving me some constructive feedback. You know, some of the shit is really negative, but that's cool too, you know, because I see where they're coming from that, and it's making me look into other areas to, you know, really come up with some more solid information. You know, I want to say proofs, but you know, it's going to be hard to prove a lot of the stuff that we're putting out there, because there's so much information and some of it contradicts what it is we've all been told. But we got to go with what we know. Okay? We got to go with what we know. So, Vivian, man, I want to thank you a lot tonight. You know, I know you got a 2-year-old just like I do, who's, you know, difficult to deal with sometimes.
And
You know, and John's great. I'm glad you guys got to meet. And we'll do this again on Wednesday. So we'll set up a time. We'll probably try to do it a little bit earlier, people. If
Yeah.
not, it might be the same time, around 7:30. And then we'll talk about super luminal signal transport. That's what we're going to talk about. Very important. It actually, it's a culmination of the stuff that John had talked about with the double slit experiment, the delayed choice quantum eraser experiment. It brings all of that together to hopefully open some eyes, some ears onto, what they may be doing with with light or something faster than light involving CERN. Okay? Other than that, people, it's been fun. It's been good. I didn't curse too much, but I'm gonna be me, man. So anybody who doesn't like me using foul language, I don't know what to tell you. I don't know you, so I can't curse you out. I'm not trying to curse out anybody. But when I start finding a lot of this information that it goes against everything that I'm learning in school right now, and it's frustrating. I mean, I'm on the side of John right now. I started reading that document. I got so pissed off. I'm like, man, ain't nothing fucking real anymore. This is all bullshit. What the fuck am I doing? You know? But, when I get to do these hangouts with you guys and, I see 80 plus people watching and listening, it comes back to me on why I'm doing this, man. Because this information needs to be shared with everybody. It does need to be shared. And I've got the time to do it. John's got the time to do it. Vivian's got the time to do it. We're actively involved in helping everyone try to explain this. And, hey, that drama shit that's going on out there, save that shit for your mama. I'm not with that. So don't email me no bullshit. Don't tell me no bullshit. Bring me some real information that I can decipher, I can read, I can review, I can put it together with whatever else we have. Okay? Other than that, man, I got nothing but love for all of you guys out there, man. Truly, I really do. So you guys be good to each other out there. Stay safe, and we'll chat at you guys again on Wednesday. All right? Take care, people. Peace.